Now that we've taken a more formal look at the idea behind a basis of our Euclidean n-dimensional space, we want to introduce another concept that's related to the basis, and it's not a difficult thing. It's just a matter of knowing exactly what this is referring to, and it's called the coordinates relative to a basis, right? Now, let me just kind of do a quick summary of our last video, meaning that let me just kind of again summarize what a basis is. So if we have a set of vectors v1, v2, dot 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 v, now there would have to be n of them if I'm going to call this a basis, right? Because that was one of the fundamental ideas that came out of the last video, is that if this is a basis, right? So a basis, and this would be for our n, right? Our n-dimensional Euclidean space. Then what it means here is for every vector in Rn, there exists unique scalars, so there exists unique scalars C1, C2, dot 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 Cn, such that C1 times V1 plus C2 times V2 plus dot 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 Cn times Vn, that will be equal to my vector V, right? So the idea of a basis is that now there is always a unique linear combination that will produce any vector or every vector in our space of vectors Rn, right? So no longer is it the question where only some of the vectors can be obtained, but now we're saying every vector in Rn can be written uniquely. That's the other key part, is that can be written uniquely as a linear combination of these vectors, right? So what will happen is this, and again, this is just kind of summarizing those ideas. If, for instance, your set consists of fewer than n vectors, so if S consists of fewer than n vectors, then it can't possibly span all of Rn, right? So then S cannot span Rn. It's just like there are too few vectors, right? So for instance, if I'm looking for a basis for R3, I can't use only two vectors to span all of R3. There wouldn't be enough, right? So in other words, think of it this way, like when you go to set up your columns, you wouldn't have enough pivots to guarantee a solution for every vector in R3, right? So if you have too few, then it will not span Rn. But there's also the problem of having too many. So if S consists of more than n vectors, then what happens is S cannot be linearly independent. So then S cannot be linearly independent. Why is that? Well, think of it this way. When you set up your coefficient matrix, right, you would have more columns, right, than you would have rows, right? Because you'd have more than n So instead of having like a 3 by 3 matrix, you would end up having like a 3 by 4 or a 3 by 5. And in that case, your nullity would be at least 1 or 2. So your nullity could not be 0. You would have at least one free variable, and then therefore they can't be linearly independent because you'd have non-trivial solutions to our homogeneous system, right? So these are important facts to kind of keep in mind, that when we talk about a basis for Rn, you know exactly how many vectors would have to be in your set. So if you have too few, you can immediately say that the set does not span Rn. And if you have too many, right, more than n, then definitely the set will not be linearly independent. All right. So when we have just the right amount, right, that's why we're guaranteed to have a unique solution, right? So there's only one set of scalars that will satisfy this requirement for the linear combination. And it is these specific scalars that we're actually going to talk about in this video. In fact, these scalars are what we refer to as the coordinates of V relative to this basis, right? So first, let's do a couple definitions, and then we'll end with some examples, right? So an ordered basis, so an ordered basis. So now we're adding the adjective ordered there. So an ordered basis of Rn is a fixed sequence. So in other words, the vectors, the order in which the vectors are written in our basis is fixed. So it's a fixed sequence of linearly independent vectors that span Rn, right? So it's a basis, but now it's ordered, and that's why it has this fixed order to it, right? So I guess probably a sequence is something that's ordered. A list is something that's ordered. A set is not ordered, right? So that's why we don't just refer to it as a set now. You can refer to it as either a fixed list or a fixed sequence, right? So if we have one of these where the order is fixed, so we can literally say the first vector in our basis, the v1, and the second vector in our basis, the v2, then this now allows us to define formally this idea of coordinates. So let's say this. So let S equals v1, v2, dot 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 vn. So now let S be an ordered basis for Rn, and let V be an element in Rn, right? And C1, C2, dot 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 Cn be unique scalars, right? And the uniqueness now is guaranteed because we're dealing with a basis. So be unique scalars such that, and again, we write down the familiar equation, but now we're guaranteed that what we're writing down is something that not only is it consistent, but it has one and only one solution, right? So such that, right, oh, I wrote my V twice, and I forgot my harpoon there. So we got Cn times Vn. So if this is the linear combination now, the unique linear combination using the vectors in my basis that produces V, we say that our scalars C1, C2, Cn are the coordinates, or are coordinates of V relative to my basis S. So of V relative to my ordered basis S. So in other words, we're referring to the word's coordinates as the scalars that we need to produce that linear combination to give the desired vector, right? And we have a nice notation for this, of course. So let me go back up. So we write, right? And this notation is fairly standard. So what we do is we put the vector v, the one that we're trying to produce, right? And we put it in square brackets like this. And then as a subscript to the square brackets, we put the letter S to indicate that this is the basis that we're working with, right? And then we say that, okay, and we actually write the coordinates in vector form. C1, C2, C3, Cn, right? So this is kind of our notation. So when we see this, we see a specific vector in square brackets with a subscript like this. It's referring to the coordinates of the vector v relative to whatever my basis is. And what it's referring to are the specific scalars that are needed in our linear combination, right? And we refer to this, right, as the coordinate vector of v relative to s, right? So we refer to this as the coordinate vector, because it's a vector now, but it contains these special scalars. The coordinates, sorry, as the coordinate vector of v relative to s, right? So again, we're defining something that isn't really new. You know, yes, we have these new vector equations, right? But we know that these are nothing more than just, you know, fancy ways of talking about a linear system, right? And the fact that we're writing it as a column also makes sense, because what this is really saying, and I'll illustrate it with the examples, is that if you form the matrix with the columns v1, v2, vn, and if you do your matrix multiplication and multiply that coefficient matrix with this coordinate vector now, you're going to get v as an answer, right? In fact, so by writing the system in matrix form, you'll see why it makes sense to write this as a column. It doesn't have to be as a column, but it's certainly consistent with everything else that we've done. All right. Okay, so let's do a few examples here. And so in these examples, I am going to be working with only bases, right? So we know that these are bases, and we're just going to be illustrating the idea of these coordinates. So let's just look at a few examples. And as usual, let's start in R2, right? So, and this is part A. And here's our vector v, and it's -2, 1, right? So here's the question. What are the coordinates of v relative to our standard basis for R2? So what are the coordinates of v relative to the standard basis of R2. Right? Well, we know what our standard basis is, right? And if we use the typical order, right? So here is the basis. And remember, it's the vector. In fact, let me write it out first using the E notation. So E1 and E2. These are our special vectors where the 1 is representing the entry in the vector that has the number 1, and then all the other entries are 0. So that's our 1, 0 and 0, 1 vectors, right? So this is the standard order that or I should say, this is the order that the standard basis is understood to be in, right? So it's basically asking you, what are the scalars that I need to combine these two in using a linear combination in order to get this vector v? Well, because you're using the standard basis, it's pretty easy to figure out what the solutions are, right? So like if I take C1 times my first vector E1, again, because that's the order, we're going to take C1 times the first vector in our ordered basis, and then plus C2 times the second vector in our ordered basis. In this case, we want to produce this vector, -2, 1. But if I put this in augmented form, it's already actually in the reduced row echelon form, because again, the way the standard basis for Rn is defined, you have a 1 in a specific entry and zeros in all the other entries, right? So if I were to write this, I mean, I'll put it in the augmented form, but you'll see right away that we know what the solution is. C1 has to be -2 and C2 has to be 1, right? So when you're using the standard basis, right, these standard, which again some of you will recognize as our standard unit vectors, it's extremely easy to figure out the coordinates that you need, right? It's essentially how much do you need to go in the x direction, how much do you need to go in the y direction, and then those are the scalars that when you perform your linear combination will give you the desired result. So what does our answer look like? Well, we're just going to use this new fancy notation and say that the coordinates of this vector relative to that basis, and we're going to write a column, and then it's going to look like exactly the same vector here, because it's going to be my C1 and then my C2, right? So when you have a vector and you're finding the coordinates of that vector relative to the standard ordered basis, the coordinates are exactly the components of the vector, right? And that's because of how the standard basis is defined, right? So you might say, like, what is the point of this? Well, this concept of the coordinates become more important when you're not using a standard basis for your Rn, for any of your n-dimensional vector spaces, right? So let's look at part B of this, and we're going to try to express the same vector but now relative to a different basis. So I'll tell you what the basis is, and I'll call this S1 since it's going to be different from my set here. So let S1 be this set. So -2, 4, and -1, 1, right? Let's actually show that this set is a basis for R2, and the easy way to do that is to show that the determinant of the matrix with these two columns, that determinant is non-zero, right? So I'll just do that quick kind of proof. So let A equals -2, 4, -1, 1. Since, let's look at the determinant of A, and in that case it is -2 plus 4. So since that determinant is not equal to 0, right, then the columns of A are linearly independent. So since I have two linearly independent vectors, then they have to form a basis for R2, right? So since the determinant is not equal to 0, A inverse exists, and the columns of A, right, form a basis of R2, right? So that's just kind of verifying that it actually works. Again, because remember what this means is whenever your coefficient matrix is invertible, your system is guaranteed to have a unique solution, and that's what we want when we claim to have a basis, right? So then let's ask ourselves the question, what are the coordinates of, I remember what my v was, it's the vector -2, 1. So what are the coordinates of v relative to this new basis, right? So relative to S1, right? Well, it's the same idea. We're going to try to find the C1 times the, now that this ordered basis means my first scalar is going to multiply the first vector in my ordered basis, and then the second scalar C2 is going to multiply the second vector in my ordered basis, and now I'm trying to produce the same vector, -2, 1, right? So clearly we can't just, I mean, you might be a little clever and you might be able to see it, but I don't think it's quite as easy to identify what the scalars are when you're using a non-standard ordered basis. But even though that's the case, we have a procedure that we can figure this out fairly routinely, and that's our system. So for instance, if we were to write this, so since I mentioned my coefficient matrix up here, why not just make use of that? So instead of doing the Gaussian elimination, why don't we use our matrix inverse to solve this? We already have the determinant. We have that nice formula for the inverse of a 2 by 2 matrix, so we can make use of that, right? If you just want to go ahead and use your Gaussian elimination, feel free. You can use any method you want to figure what these scalars are, which are going to be our coordinates. So I know the matrix is invertible, so I'm going to say that C1, C2, that's equal to the inverse of this matrix. So let me write it down symbolically first, right? So the inverse of that matrix times -2, 1, right? Now the inverse of that, so we have the determinant is 2, so it's 1 over the determinant times the adjoint, but we have that nice formula for the adjoint of a 2 by 2 matrix. That's where we switch A and D, and then we negate or we change the sign of B and C. So it ends up looking like that. And so once I do my matrix multiplication and my scalar multiplication, look, I already have it in that column form. In fact, we can even just say that this vector will actually be the coordinate vector of V relative to my non-standard basis S1. So we can even add that notation to it, but it doesn't change the method of solution, right? We're just, adding bits and pieces as we go along. So I tend to go ahead and do the matrix multiplication first. So let's do that. So if we have 1 times -2, so that's -2 plus 1, right? So that's going to be my first entry, first position, and then my second position now is 8. So -4 times -2, so that's 8 plus -2 times 1, so that's -2. So what do we have? So -1, let's see. So that's -1/2, there we go. And then we got 6/2, so this is 3, right? So there we go. So these are the coordinates of V relative to our non-standard basis, right? And if you have any doubts, you can always check, right? Let's do our check. We do the check off to the side here so we can see everything. Use a different color. So here's our check. If I take this as my C1, so -1/2 times the vector -2, 4, and then plus 3 times the vector -1, 1. Let's do our arithmetic. So 1/2 of this vector is 1, -2, and then 3 times this vector is -3 times 3, and then the sum of these two vectors, there's our -2, and there is our +1, right? So now these are the coordinates, and again, it's just a fancy way of saying here are the unique scalars that make up my linear combination to produce this desired result. And because you're working with a basis, you're guaranteed that you will always get one and only one set of scalars for every vector in Rn, right? R2, R3, and so forth. All right. So that's the idea of the coordinate vector. Nothing new, right? Because you notice we're still solving linear systems. We're still talking about linear combinations. But it's just the idea now of giving these scalars an actual name and also giving them this new notation. All right. See you in the next video.